SwayamPrabha. Digital India. Educated India.
Hello everyone, today is the last day of this week. So by now we know how to write weak form for a two-dimensional scalar field problem. We also know how to write element level equation. We have also discussed that one of the important chapter in finite element method is isoparametric formulation. Then we had also taken one simple example, and then we did manual calculations to get the solution of a heat conduction problem. What we will do today is we will write a small program. We will take the same example, but now with that program we will increase the number of elements, number of degrees of freedom, and then see what happens to the solution. Now before we start writing, the program is already written. What I will do is I will just go through the all the lines in the program so that you can understand how it is written. Now, so this was the problem, if you recall, and this problem we have obtained the solution using triangular element, 3-noded triangular element, and also using 4-noded quadrilateral elements. And with 3-noded triangular elements, we had the results. This is T4. This is the T4 because only among all these 4 nodes, only T4 is unknown. And here also among all these 4 nodes, T4 is unknown. And these are the results obtained from triangular element and also from quadrilateral element. Right? Now, before we open the program, you see, it is not the discussion on how to write a program. It is not a discussion on how to write an efficient finite element programming. Okay. Here the discussion is the code that I am going to show you that may not be the perfect code, that may not be the most efficient code, but the idea here is to not discuss that part, not look into that aspect. Idea here is to whatever steps we know, then translate them in the form of a program so that we can handle larger problem. Okay. Now, so first I will there are 2 programs I am going to show you today. One is with 3-noded triangular element, and another one is 4-noded quadrilateral element. Other than the shape function and computation of the coefficient matrix and flux and source term, all the other parts like how to define the domain, discretization of the domain, and then assembly equation, and then finally solution, and then post-processing, those parts are same. So another point, in this case, because we know that is the domain, or probably even if we change the domain for a simpler domain, we have written a small program to discretize the structure, to mesh the structure. But then, you know, this, when you actually, it is a completely different field, how to discretize the domain using different kinds of elements. These are completely different field, and there are very sophisticated algorithms available, but that's beyond the scope of today's discussion, on the discussion of the entire course. Okay, so let's start with, this is the physical domain. If you recall, our physical domain was these are the 4 points we have, A, B, C, D, and this is the coordinates of these points. Okay. Now, H is the size of the element, characteristic size of the element. So we essentially want to see when we increase H, or when we decrease H, means when we increase the number of elements, how the result converges. Okay. So h is 2 in the sense this is, in this case, h is the size in this direction, in the x direction. Okay. Now, then properties, if you recall, these are the properties we had. This is the conductivity 7, and then source term, constant source term, which is 9, and flux term, boundary flux term 15. So we can change this value. Now, this discretization part, let us not bother this part, because what I have here it is done is, because we know our domain is a quadrilateral. Okay. So what here it is done is, using the isoparametric form, the concept of isoparametric formulation, we have taken a square domain, and in that square domain we have discretizing the square domain is very easier, right? We have created several points in x and y direction, and then taking the tensor product, and then we have several points in the square domain, and then using the shape function constructed on the square domain, we map this discretization to the discretization in the actual structure. This is how this discretization is done. Okay. Once you go through this, all these programs will be uploaded on the forum. So once you go through these, things will be very clear to you. So let us not bother this part right now. This gives you the element connectivity, how these elements are connected, what are the numbering of the element. You cannot give a very haphazard numbering. We have used the policy that anti-clockwise numbering we are using. So this is how this element numbering is done. Okay. Now, so let us first, before start solving this example, so let us see how the element looks like. This is the element. The first one is, this is a two element, element number 1 and element number 2, and this is there are one node here, and then you have another node here, and then another node here, right? And element number 1, the nodes in element number 1 is defined like this. So this is 1, 2, 3 for element number 1, and for element number 2 it is defined like it is 1, 2 and 3, something like this. Okay. Okay. So if we change the size of this element, let's make it 1, our element, the discretization will look like this. Okay. Now if we keep on this, will give you the element number. So we have total 8 elements. Now if we keep on reducing the size for this, will give you the then if you further reduce it, then we get the discretization. So this will give you the discretization in depending on the what size we choose, right? Now this is how the discretization will look like. Now, so once the discretization is done, we know the element connectivity. Now the next part is the, before we start writing the computing the element matrices and then assemble them, we have to initialize those matrices, right? And before that initialization, one part is important, is the boundary conditions. We have to define the boundary conditions. Now for this, we know that this is the boundary where t is equal to 0, essential boundary, and then AB is the AB and CD are the two essential boundaries. So this is how the boundaries are defined. So EBC1 is the boundary conditions, the boundary 1 where the essential boundary condition is specified, EBC essential boundary condition, and 1 is the side 1. So this EBC1 will identify all the nodes on this line, on this boundary. Okay, and EBC2 is the EBC1 will identify all the nodes in this boundary, AB boundary, and EBC2 will identify all the nodes on AD boundary. Okay, so if we plot it, then EBC1 are all these nodes are EBC1, and all the nodes here where x is equal to 0 are EBC2, and then total EBC will be EBC1 and EBC2. So EBC and EBC are the set of nodes where essential boundary conditions are specified, and NBC is the natural boundary condition, and for us natural boundary condition is defined only on CD, and CD, the coordinate CD line can be defined as a line where y is equal to 1, right? Because this coordinate is 1 and 1. So natural boundary condition is defined as, find is a command in SCI Lab, you have similar command in MATLAB as well. So y equal to 1 means it will identify, it will search over the entire set of nodes and identify only those nodes for which y is equal to 1, y coordinate is 1, and then it will store that list of nodes in NBC. So NBC will give you the list of nodes or the set of nodes on which the natural boundary condition specified. Now, once we have defined the essential and natural boundary, next is the initialization of the various matrices before we start computing those matrices and assemble them. So for this problem, it is a scalar field problem. So every node we have just 1 degree of freedom. So size of the global coefficient matrix will be n by n. Here n node is the number of nodes we have in the system, and f is the source term. It is a vector, and the size of the vector is n node by 1, and q is the boundary flux term. This is n node by 1. Now, so and the number of element is n le is the total number of element we have, and total number of element can be obtained by this. Okay. Now, so now next is we have to take every element, write the coefficient matrix and all other vectors, and then initialization of the entire coefficient matrix and vectors are done as per their degrees of freedom. Now we have to compute these element level matrices and then populate the global matrices based on the connectivity of the element or the global node numbering of the element. Okay, so size of element coefficient matrix is 3 by 3 because it is a triangular element we are using, 3-noded triangular element, and size of FE is also 3 by 1. I1, I2, I3 are the I1, I2, I3 are the global node number which global node number for that particular element. Okay, local node number, element level node number is always 1, 2, 3, but then global node number is I1, I2, I3, which is stored in the element ELE is an array which stores the connectivity information of all the elements. One particular element, ith element of this array will give you how this element is, what are the global node numbers of the nodes of that particular element. So x, e and y are the coordinates of those 3 nodes. X. Then if you recall, for triangular for this element, our B matrix is this, and we discussed that for a triangular element, 3-noded triangular element, this is constant, right? So the advantage here is we do not have to integrate the entire thing to get the coefficient matrix. Coefficient matrix can be obtained directly. Okay, so this is J using the same formula already we know, and the Jacobian is obtained by this, and the area and Jacobian is related like this. So this will give you the Jacobian, and an area will give you the half of the determinant of the Jacobian. Similarly, we will get B, and once we have that B, our coefficient matrix will be, if you recall, this is the coefficient matrix, area multiplied by the conductivity K, then B transpose B. So this will give you the area, then K underscore con is the constant for conductivity, and B transpose B. This dash means it is a transpose. And then once this is done, it has to be once it is done, our global matrix needs to be, the global coefficient matrix needs to be populated, right? Now this now we already know what is the element level matrix KE, and these 1, 1, 1, 2, 1, 3, these are the element level node numbers. So K11 correspond to the element level node number 1 and element level node number 1. KE12 means correspond to the element level node number 1 and the element level node number 2. Interaction of these two nodes. where I1, I2 are the corresponding global node number of that particular element. So assembling has to be done based on the global node numbering. So this is the assembling. Okay, so this is already we have initialized. Then the global matrix will be this plot as we go through the loop over all the elements. Every element matrix will get populated in the global matrix like this. So the idea is very similar to what we have already discussed in case of beams and frames and other system. Idea is the same. Source term is again same. 1, 2, 3 are the element level node numbering, and I1, I2, I3 are the global level node numbering. So this gives you the source term. And the boundary flux term, here it is, we already know what is we have already identified the nodes on which the natural boundary conditions are specified. NBC is the collection of that node, and since here it is constant, we know that if it is constant, then if we integrate over any sides of an element, then it will get distributed. This flux term will get distributed equally between the connecting nodes. Okay, so this is done here. Now, once this boundary, now we have already have the global coefficient matrix, then global source term, and the global boundary flux term. Now, the next is, after that, rest of the thing is similar, whether you use triangular element or quadrilateral element or any other kinds of element. Now, so next is the partitioning and condensed to get the condensed equation. So U unknown means is a set of nodes over which the primary variables are known, and U known is the set of nodes over primary variables are known, and U unknown is the set of nodes over where the primary variables are not known. And we know the EBC is the set of EBC gives you the set of nodes where the essential boundary conditions are specified. So it will identify all the entries in EBC and then store that particular node accordingly. If the information is known, it will be stored in U known, and if the information is not known, it will be stored in U unknown. So we have this. Now then the partitioning of the matrix, same idea. We partition the matrix based on the known and unknown information, and K11, K12 are the corresponding condensed matrices. Okay. Now similarly, partitioning of the source and boundary flux term. So if known will give you the if known will give you this or the set of nodes where we have to determine the primary variable. So once this is done, then next is we need to find out we need to solve the condensed equations, and this is the solution of that. And U will give you is the set of unknown degrees of freedom. Now once this equation is solved, this EU known, then we have to put these values in the corresponding place in the global degrees of freedom. So this is done here. Now, so this is the solution. We have not yet discussed. We have so far discussed the determination of the primary variable. Now we also need to know the flux term over the element. How the flux term varies across the entire domain. So that we will determine in the post processing. So this is the solution, right? Now first let us see the solution. Okay. Before that, let me go through the program for quadrilateral element. Essentially, the entire structure is same, but there is small minor variation, and that let us discuss, and then we'll come to solution and then get the results with both the program. So physical domain, it is same. Now in case of triangular element, we had a luxury not to do any a three-noded triangular element I am talking, and not to do any numerical integration, right? We did not need any numerical integration, but now in quadrilateral element we have to we have to integrate using quadrature technique, Gauss quadrature technique. So this is we have stored all the values of integration points and corresponding weights based on the integration rule. Up to NGP is the integration rule. So NGP2 means these are the Gauss points, corresponding Gauss point, and weights are these. NGP3 means these are the corresponding Gauss points, location of the corresponding Gauss points in one dimension. Two-dimension integration means you have to take the tensor product to get the two-dimension, the points on the two-dimension space, two-dimension the parametric domain. We have discussed the same thing we will be doing here. But then if you are solving if you are using an equation, or if you see that the equation we have that requires higher order integration rule, then we can add other the values corresponding to other integration rule as well in this block. So these are the properties same. Discretization is now slight difference in the sense that time it was just only 3-noded triangle, so we had only 3 nodes of an element. Now it is 4-noded triangle, so it's a 4-node we have. So let us see the discretization here. Or discretization will be this. Okay. Now let us make it size 1. Discretization will be this. So if we make it say 0.25, corresponding discretization will be this. This is the discretization. Okay. Now so total we have 64 elements here. Okay. So next is and for the discretization idea is same in this program. We have discretized first the parametric domain and then map that discretization to the physical domain. In this case we could do it because our physical domain is also a quadrilateral. Now then it is element connectivity, the same thing. Now determination of identifying nodes on essential boundaries, it is also same. It will identify on which nodes essential boundary conditions are given, on which nodes natural boundary conditions are given. Initialization is same. Now this block is slightly different because now we have to perform the integration using Gauss quadrature technique. So the size of the coefficient matrix will be 4 by 4 because we have 4 nodes in the element, and size of Fe will be 4 by 1. Now these I1, I2, I3 and I4, these are the global node number for a particular element, where these 1, 2, 3, 4 are the element level node number. Now here what we are doing is element level node number for a particular element, an element level node number, what will be the corresponding global node number, because assembling needs to be done based on the global node number. These are the x coordinate, y coordinate. Now this loop has to be done over the integration point. So idea is we have some integration points, calculate the value, multiply by the weights, and then sum them. So this exercise is done here. So we have to go in xi direction and eta direction, in both the direction. If we are using n point rule, so n points will be in xi direction and then n points will be in eta direction. So loop will be over xi and eta both. So this will calculate what is the shape function for the quadrilateral. We know this, the expression we know, and this will give you the derivative of the shape function with respect to xi and eta. And then we know that Jacobian is equal to, if you recall, for quadrilateral, Jacobian is equal to this. So this Jacobian is can be computed. The derivative of the shape function essentially give you the and then multiplied by the coordinates will give you the Jacobian. And B matrix also, we know the expression for B matrix, and the determinant of J is this. So integration rule is, this K is a constant, then determination, this is the integration rule, if you recall, this is the integration. Now determinant of J, weight in xi direction, weight in eta direction, and then V transpose B. Similarly, the source term also will be integrated over the entire element, and this is the integration. So once that integration is done, we at the end of this loop we have the element matrices, and then finally this needs to be this needs to be the global matrix needs to be populated based on the connectivity of the elements. So this is done here. Similarly, for source term, this is the globalization of the source term. Boundary flux term, it is the same as the previous case. Now, after that, rest of the thing is exactly the same. Partitioning of the matrices based on the known and unknown information, and then finally solution of this, and then globalization of the solution. Okay. So this is the up to the solution. This is the code. So now let us get the solution. First, we get the solution with. See, whenever you write a code, one important first thing is to validate it, right? We need to see whether the result we are getting this from the code, and then we compare with some reference results so that we understand all the operations that we are performing that is correct. Okay, so let us do it for element 2 and then get the result. So solve it, and the result is this. Let us see u. What is u? Our u will be this. This is this u at the 4th node. 1, 2, 3, 4th node. So it is 0.9075 this. And let us see what was our manual calculation. Our manual calculation was this. Okay. Let us do the same exercise for a quadrilateral element, and quadrilateral element also let us take this, and then and let us see the result. U is we had minus 1.449 something, and then this was the result we have. So it shows that it is a very in this case you may find that it is very obvious because operations are very simple, so it had to match. But idea is not what happens to this problem or that problem. It is as a step I am taking. I am talking. Whenever you write a code, the first thing is the validation of the code. This is very important. Before you apply this code for another problem for which you don't know the solution, it is very important to check, apply the code program to a problem for which we know the solution, and then see whether our code gives solution or not. That is very important. Now, next is some of the important thing. Let us do. Let us start with this. So this is our K matrix, and let us find out the determinant of this K matrix. K matrix determinant is 10 to the minus 14, which is almost 0. And if you try to invert it, it will give you an error that it is the matrix is close to singular, right? Which is obvious because it is the entire matrix without imposing any boundary conditions. We discussed this, and we had seen the same thing in case of other system as well. So that's why this is determinant is 0. So we need to impose boundary condition, then only we can get the result. It can be solved, right? Okay. So now, so let us now increase the number of. Okay. Now, before that, before we see the convergence study, let us now go to post-processing part. In the post-processing part, what we will do, we will plot the result, and then we also calculate the flux term. Okay. Now, this block will plot the result, the contour. We know the nodal values, and then based on the nodes, we can plot the contour. These are the commands in Scilab, so there is no point in going through this. So you can go through this. Now, important thing is the computation of the flux term. Now, flux term is what? Flux term is the derivative of the derivative of the primary variable will give you the flux term. Here the primary variable is t, so derivative of t will give you the primary variable. So how to get this flux term? Flux term we can get from this. Okay, so this is the minus k into del t del x. We know this expression del t del n. We know this expression that will give you the flux term. Qn is equal to, so this will give you the flux term, where the b contains the information about the derivative of the shape function, and u is the values at the node. This gives you the flux term. Now, recall in this case, our shape function is a global continuity. If we see, the shape function is C naught, right? So C naught means, as we know, our primary variable. If we take at the inter-element boundary, the prime between two elements, the primary variable is continuous, and that is the minimum requirement. We had already seen it in the last week. So in this case, our variables are the approximation is C naught. And therefore, but when you calculate flask, means we need derivatives. So first derivative is not continuous across the element. I mean between two elements, right? So if you compute the flask term, then you have two elements. For instance, if you have one element here and one element here, now say here, and these are the common. This is the common boundary. This is the common boundary. So on this element, you may have flux term as Q1, and another element you may have flux term Q2. But these Q1 and Q2 may not be same. Okay, so at the inter element at this is not continuous, because that's condition we have not imposed in our while forming our approximation, right? So what we will do, we will not calculate the flux term at the nodal point, because if we calculate at the nodal point, then at this node, suppose this is node number 1, 2, 3 and 4. So 4 and 2, 2 and 4, 1 and 3. So this node number 4 we have in element number 2, and node number 4 also we have in element number 1. So from element number 1, if we calculate flux term at node number 4, we will have a value, and for from element number 1, element number 2, if we compute the flux term at node number 4, the same node, but we have different value because there is no continuity of the derivative maintained in the approximation. Okay, so we will not calculate. Does that mean we cannot get the values at the derivatives at the nodal point? We can do some averaging and smoothing. We will not discuss right now. In the 10th week, when we talk about the implementation of, again we'll be talking about computer implementation of elasticity problems. We'll revisit some of the problems that we discuss here. In that week, we will see how to do that exercise. But now, here what we will do, instead of computing that at the nodal point, which anyway we cannot do that, we will calculate at the Gauss point, at the integration point. But in case of triangular element, there is no integration point, because we did not need any numerical integration technique. So what we will do is we will calculate this at the centroid, at the center point. Okay. Now, so this is the CGLE gives you the value. I have just plotted, because at any arbitrary point you can plot, because it is constant over the element. Whether you plot it here, it doesn't matter, because it is constant. So I have plotted at a point which is defined like this. Okay. Now, so average, I have taken a point which is where x coordinate is average of all the coordinates and y coordinate is average of all the y coordinates. So this is CG, and then this QCG is this. Okay, QCG is plotted in a vector form. Just let me plot it, and then you will show them how it is plotted. So this is how this flux term is computed. But on the other hand, in case of quadrilateral element, say in this case, it is plotted at the integration point, at all these these integration points, it is plotted, right? Now we will see that. Okay, so first let us see. Let us take the. We have seen with one element we have the result like this. Yeah, with one element, let us now slightly reduce it so that we can access both this window. Okay, great. So we know what is U is this one. Okay, now let us make it 1 and then it then U is, the last one will give you the value at that node. This is not the, again, this is not the ideal way of checking convergence. If you recall, when we talk about errors in finite element method and how the errors are represented, different measures of error, one error is the absolute maximum value, means whatever deviation you have from the true solution, what is the maximum deviation, that is another error. That is one error. But another two error, whether it is the L2 norm or energy norm, it is an integration over the entire domain. We need an integration, we need a summation. So when we talk about error or convergence, it is not just at a particular point, it is how the result of the entire system as a whole converges to the true solution. Okay. So that is the true convergence and error. But here just we want to take one single point and then see how it happens to the solution at that point if we increase or okay. Now if we take 0.5, then 0.5 will give you U is this, capital U is this 0.9907, and then 0.5 our discretization was like this. Now let's take 0.25. And U is 0.1.01, and let us take further reduce it, say 1. It will take some time just to, yeah, we could have commented this plot command so that it's almost done. Yeah. So U will be 1.017. So let us highlight this plot command so that we don't yeah. So this is 1.017, and how much we got with 0.25, say let's 0.2. It was also 1.013. Let us make it 0.05. Now yeah, so this will be, you see, it is almost, now the change is very minimum. So we suppose we don't know the results of these problems or true solution of this problem. Now we kept on increasing the number of elements, or we kept on reducing the size of the element. Now we have reached a point where the further refinement, this is called refinement, mesh refinement, the further refinement will not change the result much. So if we reach that point, we say that this is a converged result. Okay, so we have obtained this converged result with, say, 0.1, h is equal to 0.1. Now, so let us plot this. This flask term. Now this flask term is, let us first plot the solution distribution of, yeah, let us first plot with this is the solution. So you see, we had imposed on this boundary, or t is equal to 0, on this boundary t is equal to 0, and this contour shows this 0, and this is the blue color. This is how the distribution of the temperature in this case. Now now let us plot the flask term. The flask term are not plotted at the You see, this is the flask term. Now, let us slightly you see, this is the flask term plotted. So, temperature, it is a direction dependent because we have x component, y component. Now, what is the boundary conditions we had given? Boundary conditions on this line, our flask was 15, defined the prescribed 15, and that was normal to this boundary, right? Normal to the boundary in this case is in y direction. And if you plot it, though it is plotted at the element, now still it gives you an idea that yes, the final solution what we are getting, and if we plot the flask, the direction it's showing the direction, it is very much consistent with our initial with our boundary condition. Now, same thing we will do with this. We'll do the convergence now. Let's plot it. This command, let's highlight, comment, so that So we have u is equal to this 1.4 minus 1.4. Let's make it 1 element size, and then check u is equal to 1 minus 1.00, and then make it 0.5. U will be minus 1.017. This is the result, similar result we have obtained from this is again almost, it's not changing much. Make it 1. It is not changing much. So you see, this when we look at this result, it is a very discouraging result, that if we change the element, discouraging, but again thought provoking, that why we are getting two different results, considerable difference in these two results. But then when we start increasing the number of elements, and then we have seen that both the cases they will give you the similar converge result. Okay. Now, so here also let us plot the let us plot with 0.25 contour, and then also plot the not this, and then also plot the so this is our contour plot. And now if we plot this, something is, sorry, this should be comment line. This is our flask, but this flask, these are plotted on the Gauss point. Now let us make it 5, then probably we can visualize it. These are plotted at the Gauss points. Let us make it 1, just one element. Then at the one element we have 4 Gauss points, because we have used 2.22 n is equal to 2 we have used. If you use n is equal to 3, say if you use n is equal to 3, then there will be 9 Gauss points, 9 integration points, 3 in this direction, 3 in this direction. Okay, and then we have seen that with 2-point quadrature rule we got the result. That's why now so this is 0.25, and then finally, and let us make it further, reduce it 0.1, and then, and this is also very consistent, though these are plotted at the integration point, but as these integration points towards the boundary, it shows you the direction of this flask is normal to the boundary. You can check what is the value. You should get the value. Let us check the value. Our value should be equal to 15, right? That was the boundary condition we had given, and the flask is flask is QGP, will give you the QGP is the gauge point. So QGP is the flask at the gauge point. So it should be Q underscore GP. It should be, you see, it is 15. X component is very small and the Y component is 14.92, which is close to 15. And that was the flask at the boundary. Our X component was 0 and Y component it was 15. So it is very consistent. It has to be consistent, but it is good to check that so that you understand all these equations, expressions that you have written in the code, they are working fine. Okay, so now you can include any other different kinds of element in this code. You can check by increasing the number of gauge point integration rule and check. Let's take, if we take 1 point integration rule, let's do the same, and the 1 point integration rule, let's see the answer. QGP is this, okay, that's good, and then U is this, but then if we have used very large element, now if you very large number of elements, but with 1 point integration, if you use, say, your deviation will be much. You can check that exercise, please do, with increasing or decreasing number of integration point and what happens to the solution. Similar, now this is a general implementation of the Poisson's equation. Now you can have, as I said in the beginning of this week, there are varieties of physical process that can be represented through this Poisson's equation. So for different cases, the interpretation of this flux term, then constant term, and then source term will be different. So you can take different problems and then see and find the results. Okay. Now, so this is the overall discussion for this week. So we will conclude this week today. Now, before that, another important thing you remember, torsion problem also can be represented through Poisson's equation, but torsion problem we will not do now. We will revisit these Poisson's problem once again in week 10 when we talk about implementation of the elasticity problem. Even though the torsion problem, whatever knowledge we have based on that, we can discuss torsion problem, but let us just wait. We will discuss torsion problem in the week in week 10. So with this, let us stop here today. See you in the next class. Thank you.